Welcome to the video lecture on transmission lines and RF system. Let's see about the second module in the second unit. I am Dr. K. Padmapriya, Assistant Professor, EC Department, Government College of Engineering, Bodi. The input impedance of the dissipationless line and open and short circuited lines. To determine the input impedance of the transmission line length L attached to a small load antenna with impedance ZA, let's consider this diagram. That is, Zn is equal to, Zn is the input impedance, whereas the L is the length of the transmission line, and Za is the antenna's impedance. So Z0 will be the characteristic impedance. So in low frequency, the circuit theory, the input impedance would be simply ZA. For high frequency cases in long transmission lines, the voltage and current will be given by the equation V of Z equals V plus e power minus j beta Z plus gamma e power j beta Z. Whereas Iz is equal to V plus by Z0 e power minus j beta Z minus gamma e power j beta Z. For simplicity, let's assume the transmission line is lossless, so that the propagation constant is purely imaginary. So if we define Z equals 0 to be at the terminals of the load or antenna, then we are interested in the ratio of the voltage to the current at location Z equals minus L. Zin of Z, that which is equal to V of Z by I of Z, is equal to V plus into e power minus j beta Z plus gamma e power j beta Z divided by V plus e power minus j beta Z minus gamma e power j beta Z into Z0. When you simplify this, we get the Zin of Z equals e power minus j beta Z plus gamma e power plus j beta Z divided by e power minus j beta Z minus gamma into e power j beta Z on the whole into impedance Z0. So using the definition for the gamma, that is the voltage reflection coefficient, the above equation can be manipulated algebraically. When evaluated at Z equals minus L, the simplified form is equal to Zn of minus L equals Z0 into Za plus Jz0 tan beta L is divided by Z0 plus Jza tan beta L. The input impedance of a load Za is transformed by a transmission line as in the above equation. So this equation can cause the Zt to be transformed radically. The power and impedance measurement on lines. The forward and backward travelling wave. The wave equations are partial differential equations of two variables t and x, and it can be solved by Laplace transform method. So by taking the Laplace transform for both V of x comma t and I of x comma t, that is the voltage and current, it depends on the two variables t and x. So with respect to t, we get, that is V of x comma s is equal to Laplace transform of V of x1 x comma t, which is equal to integral 0 to infinity V of x comma t into e power minus st dt. Similarly, the I of x comma s is equal to Laplace transform of I of x comma t, which is equal to again integral 0 to infinity I of x comma t e power minus st dt. Assuming the zero initial conditions, the two partial differential equations will become ordinary differential equation, that is ODE, with respect to the variable. So dv by dx is equal to minus s into li, whereas di by dx is equal to minus s into cv. Combining these two first order ODEs, we get the voltage wave equation as a second order ODE. So we get d square v by dx square minus s square lcv, which is equal to d square v by dx square minus s by mu the whole square into v, which is equal to 0. So the general solution for this equation is V of x comma s is equal to Vb. Vb is the backward voltage of s into e power sx by mu, and plus Vf will be the forward voltage, and into e power minus s is sx divided by mu. So where the e power sx by mu and e power minus x by mu are two particular solutions, and the Vb of s and Vf of s are the for backward and forward voltages, which will be variable with respect to variable x. Although they are in the general function of order other variable s or t in the time domain, where it will be treated as a parameter here. So these two constant, it will be determined by the boundary conditions as discussed. So the if L is the length of the transmission line, then the time for the wave to travel will be, that is t, which is approximately equal to 1 by mu, which is equal to L into square root of LC, where the speed mu is equal to 1 by square root of LC. So the whole length of the L line, L, this will be the speed which it follows. So the time will be this approximated equal to 1 by mu, which, that is L by mu, which is equal to L into square root of LC. So the above solution, it can be now written as V of x comma s is equal to the forward and backward voltage in terms of x comma s, which will be the two variables. So Vb of x comma s, which is equal to Bv of s into e power sx by mu. Vf of x comma s is equal to Vf of s e power minus sx by mu. So these are the backward and forward voltages at the front end of the line. So let's assume at 0. So Vb of s is equal to Vb of 0 comma s. At forward voltage, it is Vf of 0 comma s. So the time domain solution, it can be obtained as V of x comma t, which is Laplace inverse of V of x comma s. So similarly for both the backward and forward voltage. So simplifying it, we get Vb of t plus x by mu plus Vf of t minus x by mu. So the Vb of t and Vf of t are the Laplace inverses of Vb of s and Vf of s. So the solution for these two voltages combined traveling along the transmission line in backward and forward directions will be the following. That is, your I of x comma s is again equal to Ib of x comma s plus If of x comma s. So in time domain, if you take I of x comma t, which will be equal to Ib of t plus x by mu plus If of t minus x by mu. Reflection losses. The insertion loss is defined as the ratio of the signal level in a test configuration without the filter installed. So V1, that will be the V1, and to the signal level with the filter installed, that is the V2. So before insertion and after insertion, you take the signal level and you take the ratio of it, and that is the insertion loss. So insertion loss is a figure of merit for an electronic filter, and this data is specially generally specified with the filter. So this ratio is described in dB. So insertion loss in dB is equal to 10 log to the base 10 V1 square by V2 square, which is again equal to 20 log to the base 10 V1 by V2. So the power square is taken as 2 into 10. So filters are sensitive to the source and load impedances, so that the exact performance of a filter in a circuit is difficult to precisely predict. So comparisons, however, of filter performance are possible if the insertion loss measurements are made with fixed source and load impedances, and the 50 ohms is the typical impedance to do this. So this data is specified as a common mode or differential mode. So in common mode, it's a measure of the filter performance on the signals that originate between the power lines and the chassis ground. Whereas in the differential mode, it's a measure of the filter performance on signals that originate between the two power lines. So link with the scattering parameters are insertion loss IL is defined as follows. IL equals 10 log to the base 10 S21 modulus square divided by 1 minus S11 modulus square in dV. So this definition results in a negative value for insertion loss, that is, it is really defining a gain and a gain less than unity, that is a loss, which will be negative when expressed in dVs. So however, it is conventional to drop the minus sign, so that an increasing loss is represented by a increasing positive number. So that's the expected value. And reflection coefficient, the characteristic impedance of a transmission line, and that the transmission line gives rise to forward and backward traveling voltage and current waves. So the voltage reflection coefficient relates the amplitude of the forward traveling wave to the amplitude of the backward traveling wave. So considering the transmission line with characteristic impedance Z0 attached to a load with impedance ZL. So this is the diagram of it. So the characteristic impedance Z0 and the load impedance ZL. So ZL will be equal to RL plus JXL. So at the terminals where the transmission line is connected to the load, the overall voltage must be given by V by I, which is equal to the impedance ZL. So the expression for the voltage and the current on the line will be V of Z comma T equals V plus e power j omega t minus gamma Z plus V minus e power j omega t plus gamma Z. So I of Z comma T, which will be equal to I plus e power j omega t minus gamma Z plus gamma I minus into e power j omega t plus gamma Z. So if we plus in this equation and when we rearrange, that is V plus V minus divided by I plus minus I minus, which will be equal to V plus V minus divided by V plus minus V minus, which is into Z0. So which is equal to ZL. The ratio of the reflected voltage amplitude to that of the forward voltage amplitude is the voltage reflection coefficient. So this can be solved via the above equation. So gamma equals V minus divided by V plus, that is ZL minus Z0 divided by ZL plus Z0. The reflection coefficient is usually denoted by the symbol gamma. The magnitude of the reflection coefficient does not depend on the length of the line, only the load impedance and the impedance of the transmission line. If ZL equals Z0, then the line is matched. So in that case, there will be no mismatch. So all the power is transferred to the load. The mismatched impedance will lead to most of the power reflected away from the load. So the reflection coefficient can be a real or a complex number. Measurement of VSWR and wavelength. Standing waves. So standing waves will be produced when you have a traveling wave and a reflecting wave in the line. So assuming the propagation constant is purely imaginary, that is a lossless line, we can rewrite the voltage and current waves as V of Z equals V plus e power j beta Z plus gamma into e power j beta Z. I of Z equals V plus by Z0 into e power minus j. So substituting that, you will get e power minus j beta Z minus gamma e power minus plus j beta Z. So if we plot the voltage along the transmission line, we observe a series of peaks and minimums which repeat a full cycle every half wavelength. So if gamma equals 0.5, then the magnitude of the voltage would appear as, so this is the diagram when your gamma is 0.5, so the Vmax and Vmin is shown here. So in this case, the magnitude of the voltage will be like this. So Vmax and Vmin positions, and at 0.5 you can see, so in the y-axis, x-axis we have the wavelength away from the load. So at 0.5, so this is the point, you have the central peak. Similarly, if the gamma equals 0, then there is no mismatch. Therefore, the magnitude of the voltage would appear as, so this is the value. So your gamma equals 0. So no waveform is present. So no mismatch. So you have the perfect impedance there. Next, if the gamma has a magnitude of 1, then you can see, so this is it, the diagram, the load is entirely reactive. So while the transmission line has a Z0, that is real. So then the magnitude of the voltage would appear like this. So this is your Vmax and Vmin when gamma equals 1. So the ratio of the Vmax to Vmin becomes larger as the reflection coefficient increases. That is, if the ratio of Vmax to Vmin is 1, then there are no standing waves. So impedance of the line is perfectly matched to the load. So if the ratio of the Vmax to Vmin is infinite, then the magnitude of the reflection coefficient is 1. So that all the power is reflected. Hence, this ratio known as the voltage standing wave ratio is a measure how well matched a transmission line is with the load. So this is the ratio which determines how much it is matching with its load. So VSWR is equal to Vmax by Vmin, which is equal to 1 plus modulus gamma divided by 1 minus modulus gamma. The reflection coefficient may also be established using other field or circuit quantities. So the reflection coefficient can be given by the equations below, where your ZS will be the impedance towards the source and ZL will be the impedance towards the load, and gamma is determined at the load side, and a simple circuit configuration which will show the measurement location of reflection coefficient. So gamma will be equal to ZL minus ZS divided by ZL plus ZS. A negative reflection coefficient means that the reflected wave receives a 180-degree or pi phase shift. So standing wave ratio modulus gamma, which is equal to SWR minus 1 divided by SWR plus 1, where SWR is the standing wave ratio. Thus the absolute magnitude designated by this vertical bars of the reflection coefficient can be calculated from the standing wave ratio. That's all about it. Thank you.